Hello everyone, my name is Vishwa Kasoju. Today I'm going to talk about three-dimensional flapping flight of tiny insects using bristle wings.
For insects to stay aloft, they need to generate sufficient lift to support their entire weight. A recent study by Santanakrishnan et al. Have shown that for a solid elliptical wing undergoing constant revolution at constant angle of attack, drag increases tremendously with decreasing Reynolds numbers, while increase in lift seemed to be very minimal. Tiny insects flying at low Reynolds number in the order of 10, such as thrips, were found to overcome these large drag forces and generate sufficient lift using bristle wings and by flapping their wings vigorously at high angles of attack. Here, we show the flapping flight of large-scale insect called hawkmoth and a tiny-scale insect called thrips. From the video, you can clearly see that a hawkmoth flaps its wings in a narrow figure-eight pattern with almost a constant stroke plane angle, while thrips were found to flap their wings in a deeper figure-eight pattern and at a very high frequency. Interestingly, these wing kinematics and wing morphology are unique to these insects, but there is no proper justification for why these insects use the specific wing kinematics. Can't a fruit fly use a thrips wing morphology or kinematics, or vice versa? In this study, we wanted to understand how varying wing kinematics and how using a bristle wing affect the aerodynamic performance in a 3D flapping flight at low Reynolds numbers. Here is our robotic model mimicking the three-dimensional flapping flight in a horizontal stroke plane. The matchstick here represents the chord section of the wing with fill circle representing the leading edge and the other end representing the trailing edge. Position angle is represented using theta and the pitch angle is represented using phi. The lift was measured in the direction perpendicular to the stroke plane and the drag was measured along the stroke plane in the direction perpendicular to the wingspan. Here the lift and the drag forces measured. We obtained the hovering kinematics for various insects from previously published studies. Here are the wing kinematics for thrips taken from a recent study. You can clearly see a large variation in pitch angle during the entire wing revolution. In the upstroke, we observe a very fast pitch-up rotation of the wing, right here. Right here, you can see a very fast pitch-up rotation during upstroke. And towards the end of upstroke, the wings move with 90-degree pitch angle. For a two-wing case, this phase represents a perfect lap. Here, we present the wing kinematics for Leafminers. Similar to thrip kinematics, Leafminer kinematics have the wings to flap at high angles of attack but with more symmetrical up and down strokes. Here we present the wing kinematics for Fruitfly. The downstroke of Fruitfly kinematics looks more or less similar to thrips kinematics. However, their upstroke looks similar to Leafminer kinematics with a smaller pitch rate than Leafminers. In this study, we tested for aerodynamic performance of two wing models, a solid and a bristle wing model at two different Reynolds numbers of 30 and 120 and for three different wing kinematics of thrips, Leafminers and Fruitfly. Here, we present drag coefficient for varying wing kinematics at Reynolds number 30 for a solid and bristle wing model. Red line here represents a solid wing and the blue dashed line represents a bristle wing. For each wing kinematics, we observed the larger drag coefficient for solid wing compared to bristle wing model, and drag coefficient was found to peak during the upstroke. For each wing kinematics, you can see that the peak in drag coefficient was observed during the upstroke. Interestingly, we observed significantly larger coefficient for thrips kinematics compared to Fruitfly kinematics at Reynolds number 30. We also observed similar trends for other Reynolds numbers. Similar to drag coefficient, we observed larger lift coefficient for solid wing model compared to bristle wing model. Among the wing kinematic tested, thrips kinematics generated more lift. To understand what the forces mean and how these forces relate to vertical structures and vorticity dynamics, we perform the particle image velocimetry at different phases in a cycle along the midspan. Looking at the vertical structures at peak left in a downstroke, we observe asymmetric leading and trailing edge vertices, thereby generating net verticity moment with a strong vertex core at the leading and trailing edges of the wing. These vertices look to diffuse into the flow field. At about 50% of the cycle, where the wings start their upstroke, we observe the wings decelerate, showing zero net verticity moment, thereby generating no lift. At position where we observed the peak lift coefficient, we found that due to the faster pitch of rotation during the upstroke, we found peak in lift coefficient due to the formation of very strong diffused leading edge vertices. Comparing Reynolds number 30 and 120 for a solid wing model for thrips kinematics, similar to Reynolds number 30, we observed stronger leading edge and trailing edge vertices for a solid wing at Reynolds number 120. However, we observed the leading edge vertex to be elongated right here. It looks elongated at Reynolds number 120 compared to like a more coherent, strong vertex at Reynolds number 30. Comparing a solid and bristle wing model at Reynolds number 120 for thrips wing kinematics, we observed formation of leading edge vertex for a bristle wing model with a vertex strength looking a little weaker compared to a solid wing model. Here we are looking at average drag coefficient throughout the cycle for three wing kinematics at Reynolds number 30 and 120. Overall, we see noticeable drag reduction for bristle wing compared to solid wing at Reynolds number 30 compared to Reynolds number 120. For Reynolds number 30, represented in red color, Leafminer kinematics showed lower drag coefficient. For Reynolds number 120, represented in blue color, Fruitfly kinematics showed lower drag coefficient. Looking at average lift coefficient, Leafminer kinematics generated more lift at both the Reynolds numbers. Finally, looking at average lift over drag ratio plot, it is evident that Leafminer kinematics offers significant benefit in increasing the aerodynamic performance of both solid and brittle wings at both the Reynolds numbers. In summary, for a fixed wing morphology, at both Reynolds numbers of 30 and 120, we observed Leafminer kinematics to perform better in generating more average lift coefficient compared to other kinematics. However, from time series plot for lift coefficient, we saw that peak lift coefficient to be more for thrips kinematics compared to Leafminer kinematics. We suspect that this is due to large stroke amplitude for Leafminer kinematics compared to thrips kinematics, in addition to small variation in non-dimensional pitch rate between thrips and Leafminer kinematics at the start of downstroke and end of upstroke. Finally, in conclusion, we want to specify that Leafminer profile offers significant benefit in increasing the aerodynamic performance of both solid and brittle wings at Reynolds number 30 and 120. And for a brittle wing model showed similar aerodynamic performance compared to a solid wing model for all the kinematics at Reynolds number 30 and 120. Note that all the results presented here are for single wing performing flapping motion. For future studies, we want to verify the aerodynamic performance of these kinematics for a wing pair performing clap and fling motion. And thank you. And if you have any questions, please come to the session. Thank you.